This lesson is on how to use stoichiometric calculations to determine the percent yield of a particular reaction. You can kind of guess how this usually goes, as in the alternative title for this is You Don't Always Get What You Want. So I have two anecdotes. One is a poem and one is one that actually happened to me, so I'm going to read through them. If you don't feel like listening to it, feel free to skip forward. So the first one is a poem that I found when I was reading some chemical literature somewhere. It's by John Hanson. It's called "'Twas a Night to Make Crystals." So 'twas a night to make crystals, and all through the hood compounds were reacting as I'd hoped that they would. The hood door I'd closed with the greatest of care to keep noxious vapors from fouling the air. The reflux condenser was hooked to the tap, and the high vacuum pump had a freshly filled trap. I patiently waited to finish my task while boiling chips merrily danced in the flask. Then from the pump there arose such a clatter that I sprang from my chair to see what was the matter. Away to the fume hood, up at the door, and half of my product foamed out on the floor. Then what to my watering eyes should appear but a viscous black oil which had once been so clear? I turned the pump off in a terrible rush, and the oil that sucked back filled the line up with mush. The ether boiled out of the flask with a splash, and hitting the mantle went up in a flash. My nose turned quite ruddy, my eyebrows went bare. The flask singed off nearly half of my hair. I shut the hood door with a violent wrench as acid burned holes in the floor and the bench. I flushed it to water, and to my dismay, non-sodium hydride had spilled into the fray. And then the fire got way out of hand. I managed to quench it with buckets of sand. With aqueous base I diluted the crud, then shoveled up 7 big buckets of mud. I extracted the slurry again and again with ether and then with dichloromethane. I can't get that to rhyme. Chromatographic techniques were applied several times till the product had been purified. I finally viewed with a satisfied smile 1/2 gram in a shiny new vial. I mailed the yield reports to my boss, 90% allowing for loss. Good work, said the boss in the answering mail. Use same condition on a preparative scale, which means make more of it, use the same conditions. So that wouldn't work. The next one is something I call reactions behaving badly. This happened during an AP chemistry class around about 2012. And things went so badly, I had to send out emails to all of the parents to make sure that they knew that their children were safe the entire time. So, today's lab was such a case of reactions behaving badly that I just got to share. The objective of the lab is to determine the amount of copper in new pennies, about 5%. Yesterday, my students weighed their pennies, then mangled them enough to expose the zinc core. Some of the guys got kind of carried away with the mangling, actually managed to cut a penny in half almost cut a penny in half with a pair of wire cutters that I'd brought in. I tried the lab out myself earlier with 6 molar hydrochloric acid, but the reaction rate seemed a bit slow. I noticed that we had some muriatic acid, which is 9 molar hydrochloric acid, so I decided to let the kids use that stuff straight out of the bottle. This was mistake number 1. They had trouble pouring the acid, which turned out to be badly discolored and fuming essence of chlorine like mad. I should note at this point that the exhaust fan for the room doesn't work, and that the fume hood that I have seems to be blowing the fumes back out into the room. They ended up using an excessive amount of the foul stuff, leaving my room yesterday smelling like a pool gone wrong and all of my exposed skin itchy. This was mistake number 2. Today they came in and I told them to separate the leftover acid from the copper chunks that were remaining. Then dissolve the copper in 5 molar nitric acid, which had proven to be relatively tame when I tried the reaction with my penny. We learned a number of things during this phase of the experiment. It is necessary to use a funnel to support the filter paper if you decide to filter your copper. It is impossible to get the copper fines off of the filter paper. Hydrochloric acid gives off enough fumes to make some people break into hives, and we should never, ever use muriatic acid ever again. The next step entailed dissolving the copper solids in nitric acid. Now when I did it, it was a very boring reaction. A little bubbling, a whole lot of stirring and poking on my part with a nice light blue solution forming after about 15 minutes. When the kids did it, now that was something else altogether. Initially, it was just like my penny, some fizzing, a lot of questions of, is it supposed to be doing something? And then the beginning of the formation of the light blue color. This is when things deviated from my experience. Once they started to get that light blue color, most, but not all, of the kids' reactions went berserk. They started fizzing like mad and giving off that nasty red gas that gives smog its eye-burning quality. Keep in mind that there are still kids trying to get their copper out of the stinky hydrochloric acid solution. At one point, I see a flash of light from a group of boys that like to push the limits of acceptable behavior. They all say, "Whoa," and start backing away from their lab station. It turned out to be just a reaction to the runaway nitric acid fizzing. Actually, what they'd done was they'd spilled nitric acid on a rather dirty hot plate, which had then made a TNT kind of compound, which had gone off. They were really lucky that nothing else happened. But for more than a few moments, I was convinced that they'd managed to do something truly stupid. So after they got through the nitric acid step, they were supposed to transfer their sample to a flask and add enough ammonia to turn the solution dark blue. Unfortunately, some genius in the past had ordered a whole bunch of the flasks that we had to use that were made out of dark red glass, complicating seeing the final dark blue in solution immensely. The first student that got to this point added the amount of ammonia that I'd used on my penny and then brought the flask over to me. Her solution had formed a clump of white stuff in the bottom of her flask. We found out that by adding more ammonia to it, it would cause the clump of junk to dissolve, so I told her to keep doing that until the solution appeared to be clear, not cloudy, at least as best as she could tell when holding it up to a light. Keep in mind that there are still students trying to get their copper out of the stinky hydrochloric acid solution, that there are students with nitric acid reactions that are fuming out red smog smoke, and now add concentrated ammonia, way stronger than the stuff you can buy at the store, into the fray. The ammonia fumes started reacting with the hydrochloric fumes and forming a white smoke, causing most of the kids to run to the open window to breathe. I think mistake number 3 was letting the kids get started on the ammonia step while they still had the fuming acids out. Fortunately, we ran out of time. Tomorrow, the rest of the kids will finish off with the ammonia, then go on to the presumably non-stinky portion of the lab. At least that's the way it went when I did the experiment. So this is very definitely an example of where things do not go the way you expect them to. So this one, we have one of my favorite reactions. It's going to be the synthesis reaction of ammonia, NH3. And we're going to start out with 2 liters of nitrogen, and using the coefficients, we know that that's going to require 6 liters of hydrogen gas in order for the reaction to go to completion. On the graph, we have the initial hydrogen concentration, which is going to be up here near 6 liters. We have the 2 liters of nitrogen shown, and then we have 0 liters initially of NH3. So we go ahead and we mix everything together, let it get started. And we can see after a certain point in time, the reaction stops, the reaction concentration stopped changing. And so instead of the calculated 4 liters of ammonia that we should have formed, we only made 2 liters. So what we could do is we could calculate the percent yield. So that is going to be what you actually got. That's the experimental yield. You have to be given this in a problem. You can't extract it with, just by looking at a piece of paper, divided by the theoretical or the calculated yield times 100. So putting in our numbers, we actually got 2 liters. We thought we'd get 4. So that is an example of a reaction that only goes to 50% completion. So here is an example where we're going to actually do a grams to grams calculation using a stoichiometry chart. And then we are going to determine the percent yield. So we set up our stoichiometry chart. So we know that we have 2.5 grams of hydrogen gas, and we want to figure out how much water vapor it'll make. So we got to determine how many moles of hydrogen gas we have present. So we take our 2.5 grams and divide by 2.016 to get the number of moles. This is a 2 to 2 relationship. So that means it's going to be the same number of moles of water are formed. So now we have moles multiplied by the molar mass, and we get that our theoretical yield is 22.4 grams. It said instead we did not get 22.4 grams, we only got 18 grams. So we determine the percent yield, do 18 divided by 22.4, and we get that it was a little bit over 80% yield. So a pretty good yield. So this is an example from the worksheet that goes with this lesson. So our first step that we want to do is we want to balance the reaction equation. And so when you balance it, we see that we have coefficients of 1, 2, 1, 2. So the next step would be to set up a stoichiometry chart. Make sure you put the substance, the grams of the ammonia underneath that particular substance so you don't get confused with the proportionalities. So we're going to put grams there. So that is 13.6. And we are looking for how many grams of the platinum compound, which is called cisplatin. It's one of the earliest chemotherapy drugs that people found. There we go, switching pens. All right, so the next line in the stoichiometry chart is molar mass, GFM. So the molar mass of ammonia is 17.031. We do our division and we get that this works out to be 0.80 moles worth of ammonia are initially present. So now we got to do our conversion. Try to make a habit of using arrows to attach your moles of reactant to moles of product, because this is a really good habit for when we start talking about limiting reagents. So this is a 2x to 1x relationship. So we want to divide by 2 because we only want to have 1x. So this we have 0.40 moles of the cisplatin. And then we multiply by its molar mass, which is 300.052. So we do the multiplication and we get that our theoretical yield is 120 grams. So now the next part, it says that we isolated, so that tells us what our actual yield is, 44.4 grams of the cisplatin. So we have 44.4 divided by our theoretical, which is 120 grams. Put my units in. Times 100. And this one works out to be a very low yield reaction, which is unfortunate considering how expensive platinum compounds are. You don't want to waste any of that potassium platinum compound. So this is only a 37% yield. All right, so just the main mistakes that people make is they start putting their actual yields into the stoichiometry chart. Remember, if it says that it yielded or if you isolate it, this is the actual yield, and the only time you're going to use it, I'm going to write that above it. The only time you're going to use it is when you go to calculate the percent yield. All right, thanks for listening.